好咁啊，聽到同埋有冇回音啊？應該冇啊。我又唔記得咗邊個掣。好，咁啊睇下同學聽到啦。呢度，OK, thank you。好，咁啊幾多同學？哇，幾多？10幾個。好，咁啊啲測驗我應該都冇乜問題啦，係嘛？都正路啦，係嘛？咁啊，今日主要都係講 foundation。我睇下我哋嘅 schedule 跟進成點先。我哋嘅 schedule 應該都完美嘅。今堂就係啦 ，show foundation。 assignment 2係幾時？咁或者今堂都如果有時間講下 assignment 1做翻啲準備工作。assignment 2就assignment 2係11月12。係喎，咁啊一個禮拜後有19號又係個 lab report 咯。OK。好，咁我哋就係啦，講咗個 shell foundation 先啦。Since we'll start recording. Okay. Recording has started. So we'll move on to the our next chapter, which is the foundation design, or to be specific, this is called the shell foundation. So we start with shell foundations, which is this one, or sometimes we call it the bearing capacity. So this is the shell foundation, or sometimes we call it the bearing capacity. The reason why we call this shell foundation is that besides for foundations, besides shell foundations, we actually have a deep foundation, which is sometimes we call it piles, okay, so that's why we differentiate this as the term and use the term shell foundations. So, you are expected to be able to justify the use and design appropriate foundation systems. So, for a shell foundations, we actually has the number of systems like a very small foundations, which is called a footing or a pad footing, or a very large foundation, which is called a raft foundations, etc. And we also have a square foundation in the shape of a square, or foundation is a very long foundation, which is sometimes we call the strip foundation, etc. So there are various kinds of foundations. First of all, various shapes of foundations, and we also need to still remember we have two major types of shear strength result. If you still remember, one is the undrained shear strength. This one actually calls for phi equal to 0. And then we have the effective stress, or sometimes we call it sometimes we call this the total stress analysis. Total stress analysis, and this is effective stress analysis. If you still remember this too. So for this one, we use the undrained shear strength. For this one, we use the drained shear strength, or to use the effective shear strength. Probably don't remember when to use this and when to use this. Do you still remember? So this has to do with time. So this has to do with time for fine-grained soil. So I repeat this many times. Fine-grained soil. So how does the fine-grained soil different from the coarse-grained soil? It's about the water. The time for water to be to escape from the soil. So in the short term, so in which case the pore water pressure will build up. Then sometimes then they use the total stress analysis and use the undrained shear strength. And for long term, or for, I'm talking about fine-grained soil, okay? For fine-grained soil. And for long-term analysis, then we will expect the excess pore water pressure to dissipate or to change. And we will use the effective stress analysis. So this is the idea. And then for coarse-grained soil, then we always use the effective stress analysis. So for coarse-grained soil, basically we will use this. But for fine-grained soil, depends on whether it's short-term or long-term, then we have to decide what types of shear strength we will use. I hope by now then you have a more understanding of this concept. So very good. This is a textbook, or you can also read the book by Gray, which is as lots of examples as well. And of course, this is a very good, excellent reference published by the Geotechnical Engineering Office. And also there's a reference, you can, sometimes you can make reference to the Code of Practice for foundation. I think it's the 2017 version. Okay. So this is available in the under the buildings department. So you can make reference to that. Okay. So this is some of the shell foundations. You can see this is a very simple. We call this footing or packed foundations. And sometimes the foundations will be connected to form large foundations. Sometimes we call this a raft foundation. Okay. So in this chapter, then we will look at the basic concept of the Terzaghi's bearing capacity theories, and we look at the factor of safety. In general, we are still using the global factor of safety in Hong Kong, but there's also a trend to move to partial safety factor as well. And the effect of groundwater on how to use these equations. And nowadays, we will actually use the general bearing capacity equation. So if you look up the core practice for foundation, so this is the equations that you will see in the core practice. And we'll also look at the effect of eccentricity. For example, sometimes the fact that the load may not act at the middle of the foundations, which the loads may be acting away foundations. One of the reasons for this is that actually there's a moment. The eccentricity in some way can be considered as a moment， 係嘛？即係我哋除咗個 foundation 可以 add 落正中心，梗係最好啦。但係其實有機會有 moment 㗎嘛，係咪？即係you actually design a buildings resting on foundations, then you will expect there will be vertical load, shear load, and then a moment on the foundation. So this is a way to cater for the eccentricity. You may also consider it as a moment acting on the foundations, because this eccentricity will actually give you a loading times a moment arm. So P times eccentricity is actually will give you a moment. So this is quite common for a foundation to resist a moment. Okay, so let's see any question here. So far, no questions. Again, we have a lab in the coming Saturday and also a computer workshop in the afternoon. So for those who haven't shown up last time, for example in here, 有啲同學上次都冇返，好似有個梁同學。有冇其他？李同學都係喎，梁同學、李同學上次冇放，阿莫同學，呢個都有幾個冇放。咁上次唔舒服嗰啲，今次可以返啦。So we move on to the Terzaghi's theory. And again, first of all, we look at the shear strength. So the bearing capacities actually depends on the shear strength of the soil, which we will do a lab test this coming Saturday. And the shear strength is actually represented mainly by this relationship, which consists of a cohesion. Actually, this is the term we used to use. In fact, this is only a line intersection. So what happens is that if we put a normal stress against shear, will sometimes, in most cases actually, we'll get a straight line. So we have an intersect, what is called an intersection. 即係一個 cut 到零個位嗰個啦 and also a friction angle. Okay, so we used to call this cohesion, but bear in mind that whether or not there's true cohesions, it actually depends on different cases. But anyway, so in this case, in most cases, actually the shear strength can be, so this is the shear strength, can be represented by this relationship, a cohesion plus a friction, and the friction depends on the normal force. Okay, so this is the basic. I assume that most of you are aware of this. This is very basic. So if we conduct this in a, we can actually express this this relationship in terms of effective stress as well. So if we conduct the test and analyze the result using effective stress, then we can express this into the effective stress as well. Okay, so basically the same. The values may be different, but the relationship will be the same. Okay, this is the effective stress relationship. So first of all, we actually have to look at the failure mode. So how does foundation fail? So the foundation will fail under 3 failure modes, which actually depends on the stiffness or the stiffness of the soil. So if the soil is very soft, so you will expect the foundations to actually punch through the soil. 即係如果呢啲好似豆腐咁樣，係咪？咁佢個 foundation 就會一打入去就壓穿咗 punch。Whereas if it is a compacted sand, when it fails, you will expect the foundations to fail like this. Okay, so there are, first of all, we have to understand there are 3 failure modes. So this is the 3 failure modes. So this is when the soil is very compressible or highly compressive, then you expect the failure mode to be like this, punching through. Or if the soil is in compacted state, so when the foundation fail, you will expect the foundations to and then fail like this, like the rotation along here. 唔知同學睇唔睇明呢幅圖啊？呢幅圖咧，因為畫咗兩邊嘅，其實咧就即係淨係應該係睇一邊，睇下咁啊都就，因為佢畫晒，因為個 foundation 可以咁 fail 又得，咁 fail 又得係咪？所以佢畫咗兩邊。咁其實咁佢如果你得邊嘅話咧，個 foundation 就係咁樣，即係個 foundation 就即係咁啦。咁佢 fail 嘅時候咧，就呢個係咁噶，就咁樣。呢個明唔明解啦嚇？咁呢個就係嗰個標定或者嗰個 foundation，OK， 即係大啲啊咁嘅。但係in all the books they like to express it this way because this is the foundation can fail. This way, it can also fail that way. So in most of the book, it is drawn That's right. So some of you may be mistaken what that means. Okay. So compare with this one, you will see this is a puncture because the material is very soft. So you expect this is what is called the puncture shear failure, and this is called a general shear failure. And our discussion actually is mainly on the general shear failure. So of course, there's another conditions. For example, if the soil is loose, then it will fail something between the two. Okay, so again, it will fail by a failure surface, something like that. So this is basically three types of failure mechanism, and this is the one we will look at more. And for this one, the theory developed for this case will be modified and then can be used for this case. And for this case, then there may be some other methods. Okay, and maybe in this case, the failure is actually controlled by settlement. So our discussion is mainly on this one. Okay, the general shear failure. Actually, the mode of failure actually depends on the density of the soil. So if the soil is very strong, very compacted, meaning that the density or the relative density is very high, close to 1, then it falls into this mode. So if the relative density is very soft or is low, then it falls into this mode. And then somewhere in between, it falls in this mode. Okay, so this is a study found by this gentleman here. So in your design, therefore, before you apply the theory to it, then first of all you have to understand the what mode will the foundation fail. Okay, so if the soil is very soft, then you need to use this type of method. If the soil is good enough, then you will expect to use this method, and so. Okay, so before you do any design, then you need to understand what types of failure mode based on some research by other people. And this is again another result showing the relationship of the unit weight with respect to the failure mode. So this is based on the general failure shear mechanism. And the basic concept is that you have a foundation. Again, this diagram is drawn on two sides because you will expect actually in your case the foundation will actually fail like this. Okay, so it includes actually 3 components. So it assumes that this is the foundation, and when it fell, it pushed, and the soil fell along this plane, and then it also push this soil up. Okay, and when the soil fell along here, So if you have two components, one is cohesion, another is the friction, because the shear strain has two components, so you will expect the formula to include the cohesion and also the friction. And then on top of that, we actually, to fail this foundation, is necessary to push this soil up. Okay. So it is actually similar to pushing a soil upward. And the definition of shear foundation is that the depth, 即係個深度啦嚇 should be less than 3 to 4 times the width. So in this foundation chapters, so this term B usually refer to the width of the foundations, and this D usually refer to the depth of the foundations. So you will expect if your foundation is constructed much deeper, and when it fails, it needs to push more soil up. So you expect the bearing capacity of the foundation will be higher. Okay, so again, this is the solution obtained by Tesakis for a strip foundation. Okay, so remember that this foundation, this equation is for strip foundation, or sometimes we call it continuous foundation. Okay, so this means that the foundation is very long, just like our retaining wall. Okay, just like our retaining wall. So in this case, it actually consists of 3 components. The equation actually consists of 3 components. So this is the first component. So you can see it has to do with the cohesions, and then there's other components, and you will expect this to one of this is related to the frictional, to the friction, and one is related to this, we call it overburden. So you can see in this equation, if the cohesion is high, so the bearing capacity is high. And again, this Q, we call it overburden or surcharge. Overburden or surcharge. So some folks use overburden, some folks use surcharge. So this Q is actually the amount of soil. So if the Q, the surcharge is high, then the bearing capacity is high as well. And then we also have this components here. And you can see when I said previously, the equation should actually depends on the friction angle, right? So where does the friction angle appear? You will see that we have 3 factors here. We call it bearing capacity factors. And it is actually a function of the friction angle. So that the friction angle. 因為呢個 friction angle 咧就影響咗佢嗰個 slip surface 嗰個 profile， 即係例如個 friction 同咧，可能呢個就係咁啦。咁啊，第二個 friction 咧，嗰個 slip surface 就會影好咗嘅啊。咁理論上，如果係 friction angle 係零嘅話咧，咁個 slip surface 咧就 more like 嘅circular， 即係好似 undrained 咁啦，就好似係一個半圓形咁樣，或者係 circular 啦，我哋。Okay, so this actually is given by a series of formula. So I don't know where. So this is each of this bearing capacity factor is given by this formula. Okay, so you must be very happy with this formula. Okay, must be very happy with this formula. Okay, and it actually just maybe depends on the friction angle, you see. So some people is kind enough again to prepare a table. So it actually calculates all the bearing capacity factors for you, provided you have the friction angle. So if your friction angle is say 30, then you can obtain this values immediately for Tesaki's formula. Okay, so this is for Tesaki's formula. Okay, and I also want to briefly go through these assumptions in the Tesaki's bearing capacity theory, and in the Tesaki's bearing capacity theories, and it is important to know the depth again because this is a shallow foundation. Okay, so the depth of foundations is less than or equal to its width. And there's no friction on the base of the footing. The base of the footing is rough. Okay, meaning that then if the assumption is valid. And soil above and bottom of foundation has no shear strength, so it just gives a surcharge load. The surcharge is considered, and the load is vertical, non-eccentric. Homogeneous, of course, is always for basic formula is typical. The soil is homogeneous and isotropic, and it is assumed that this formula is for strip foundation, meaning that the length of the foundation is very long. So this is some of the assumptions. So sometimes we actually need to know the assumptions, and otherwise, in cases where actually these assumptions are not valid, then we have to think it again and using the formula. Okay, so this is all the equations for the bearing capacity factors, and then some people is kind enough to build these tables so that we can easily obtain the values. Of course, nowadays with computers and very good calculators, then we can obtain these values quite easily. Okay, these are for strip foundation. So how about for square foundation or for circular foundations? So some people can provide these two relationship. This you can call it a modified or modified equation. So for square foundations, 呢個變咗立體喎 ，square foundation 啊，即係頭先 strip foundation 咧，就其實係一個數學嘅演繹係嘛，即係 2D 嘅係嘛？如果你個 foundation 好長咁，其實就係好似一個 2D 咁樣，你 cut 任何一個面係嘛？但係如果係 if it is a square foundations, it's actually more of a 3D effect 啊。Same for circular foundation. So we need to modify the basic equation. So in this case, the basic equation is modified. So instead of 1, it is 1.3. So instead of 0.5, it is 0.4, etc. And then for circular, again, is modified. So this is how we deal with other shapes when using the Tesaki's equation. And then again, the discussion above actually is based on the failure mode, the general shear failure mode. So how about the local shear? How about the soil is loose and the soil is soft? So we have to, so the general shear concept doesn't work, so we have to again modify it. So if it is a local shear failure, then we have to reduce the friction angle, and also we have to modify this formula appropriately. Okay, and we have to use, because the friction angle has been changed, so we actually have to use either you use the basic equation to recalculate it, or you have to use this modified table. So this is the modified table. This is table 3.2, and this is for local shear. This is for local shear. Okay, so this is how Tesakis has managed to deal with general shear and local shear. Of course, there's also limitations for the Tesakis, and that is actually, if you look at the equations, there's no consideration for depth, no consideration of inclined load. Inclined load 係咩意思啊？打斜嘅 load 係咩意思嚟嘅？ Because we always in the development, the loading is assumed to be vertical, right? So what does inclined load mean? Inclined load actually also means there's a horizontal load, right? So we have a vertical load, we have a horizontal load, so this will actually resolve into a inclined load. So in practice, for a foundation, so you expect, again, as I have said, you expect to have a vertical load, and then horizontal load, and then a moment. So when designing a foundations, then we can actually use a eccentricity to simulate the moment, and inclination to simulate the horizontal load. Okay, and there's no consideration for a shape. For example, if the foundation is rectangular shape, So there's no such consideration in the Tesaki's original formula, because the formula so far has just handled strip foundation, square foundation, and also circular foundation. But there's no what happens if the foundation is rectangular shape. So there's no consideration. So the next, okay, we talk about the factor of safety first. The factor of safety actually because when we construct the foundations, so we usually apply the load here, and then we find the ultimate bearing capacity, right? So the factor of safety then will be the ultimate capacity, which is calculated from the formula, divided by the foundation, by the actual load of the foundations, then you can get the factor of safety. Okay? So this is one way of obtaining the factor of safety. But however, in some cases, the foundations actually consist of digging into the ground, and this volume of soil is actually removed from the foundations. So sometimes the factor of safety is calculated based on the net bearing capacity. So instead of just calculating the ultimate bearing capacity, we minus the soil removed and then divided by the actual foundations. Also, again, we need to minus the soil removed. This is the soil removed. So this is calculated based on a net. This is a net. Okay. So there are, you can see there's two ways of finding the factor of safety. Okay. One is based on the gross ultimate bearing capacity. The other is based on the net ultimate bearing capacity. Okay. Okay, so we have an example here using the Tesaki's method. So in this case, we have the square foundations. Remember, for Tesaki's formula, the formula is for strip foundation. It's for strip foundation. So this is the square foundation. So you have to multiply. We have to use the multiply formula. So this is the multiplied formula. Okay. And then friction angle. So how do we use this friction angle? We use this friction angle to find NC, NQ, and N alpha, or whatever. Okay, so we look up the table and then find this, or you can also use the equations to calculate this, either way. So you can find these factors. Okay, and the first step is to substitute into this equation. So this is very straightforward. With B, again, is the width of the foundations. This is the density of the soil. And this is the cohesion. So the cohesion is given. And then the next one is to calculate this, Q. So what's Q? Q is actually the overburden. 或者佢係叫做 effective surcharge。effective surcharge 係咪？所以咧，咁啊要好簡單啦。咁啊佢個 foundation 藏咗落個地下度幾多米啊？照計啫，佢藏咗落上位。So it is 1 meter below the ground, and this is the density of the soil. And you know the surcharge， 即係呢個即係中間呢個 term 咧，中間嘅 term 我哋叫 surcharge 啊，個意思咧就係佢要 fail 嘅時候咧，其實佢係要將呢嚿泥咧 push 上去，咁所以呢嚿就係嗰嚿啦，咁啊變咗 depends on 呢個 surcharge 啦，我哋通常叫或者叫做 overbearing。So just by substituting all these values into this formula, then we get the ultimate bearing capacity of the soil. And if the factor of safety is 4, so we can calculate the allowable bearing capacity of the soil. So this is the allowable, the actual loading we can apply. So from here, if we know the area of the foundations, then we can calculate the force. So the area of the foundation is 1.5, 1 times 1.5, so we can actually calculate the force that it can support, meaning that this is the foundation, and for example, if this is the column, then this column can support 292.5 kilonewton. And this foundation is 1.5 times 1.5 meter. Okay. So this is the an example showing how to use the Tesaki's theory. And other examples is to assuming that the soil is loose, and then in that case, then you may have to use the local shear failure mode. And again, we have to use the modified equation and also the modified factors. So there are two things that are modified. The equation itself is modified, and also the all these three bearing capacity are modified. So you have to look up another table, which is table 3.2. But the rest of the concept is just the same. So by using the same examples, but then because this is a local shear failure mode, and then we calculated that the ultimate bearing capacity is only 237 compared with 520. So it is almost half. And again, you can see the load is again is much reduced. 即係因為佢係 local， 即係個泥土比較 loose 啲啦，咁啊變咗咧就渣啲咯，渣啲咁佢個承托力就低啲啦嚇。So these two examples actually can give you how this type of how to apply the Tesaki's formula in the shell foundation design. And then the next topic then will be the effect of water. Actually, the effect of water is quite interesting here because water can be, so this is again, this is what we call the design water level. So the water level can be at the top. The water level can be above the bottom, and the water table can be far below, or the water table can be somewhere in between. So there are actually three different cases. 1, 2, 3. So there are actually 3 different cases. So how does this, how do we apply, or how does water affect the use of bearing capacity? So we again look at the basic concept of the bearing capacity. If you still remember our bearing capacity ultimate, so this is the symbol we use. This is the symbol we use. Still remember? So we have three parts, right? So this is the 3 part. So how does water affect this 3? Or how does water affect this formula? So you can see this Q is actually the overburden pressure. So this actually has to do with this. And again, this term has to do with this, right? So this is how water can affect this, because if you still remember effective stress concept, right? So if there's water, then we will use the effective stress or the submerged density, or to use the effective weight. So it's the same concept applied here. So we actually have 3 cases. So case 1 is water is between here, right? So water is either here or here, okay? So what unit weight should I use for this term? Because if the water is here, or here, or here, all this will be submerged, right? Submerged, right? And what is the actual meaning of this term? 記唔記得呢3個 term 係咩意思啊？呢個 cohesion 啦，咁啊水對呢個冇 effect 喎，反而啊水對呢個冇 effect， 因為裏邊都冇嘢，因為呢個同 friction angle 有關，呢個 cohesion 啊嘛，其實水係對呢個冇影響，但係水對呢兩個有影響，因為個 density。好啦，記唔記得呢3個 term 係咩意思啊？cohesion 啦 ，overburden 啦 ，overburden 就係呢嚿嘢啦。同埋呢個係 frictional slip 嘅意思咧，就係呢度 assume 有個 slip surface， 就係 below 個 foundation 喎，你記住下呢個 slip surface is actually below the foundation. Okay? So for case 1, so the water varies from here to here, but below the foundation is actually always saturated. 係嘛？呢度全部都浸水嘅。So in this case, we always use this， 即係減咗水嗰個浮力。So you can see, we always use this for this case。即係你要明白佢每一個 term 係 for 咩 purpose， 咁你係容易理解啦，係嘛？所以你見到咧 ，case 1 is always submerged， 永遠浸起水嘅。喂，佢呢個係 for 呢個 slip surface。OK， 咁呢個咧就點咧？呢個直接計咯，好似我哋計 effective stress 咁計咯。 如果佢浸晒落水嘅，咁咪照逐嚿計咯。咁啊呢個嚟呢個乾泥，乘翻個深度。咁呢個浸咗落水嘅，乘翻浸咗落水嗰個高度咁樣，照 effective stress. So for this term, the effect of water will actually affect the effective stress. Okay, and for this term, for case 1, because if water is above the bottom of the foundations, then all this is submerged. So it's always submerged. So this is the idea. And then for case 2 就係呢個啊，呢個麻麻啲啦。咁啊講咗 case 3先啦。case 3咧就係個水位低過呢個，咁啊容易啲啊，呢個簡單啊嚇，我都估到啦，水位低過呢個，冇明顯全部都係乾泥啦，全部都係乾泥。So this is so we use the bulk unit weight. We use the bulk unit weight here. Bulk unit weight 或者乾泥啦嚇。Okay, so this is very straightforward. Case 3, and case 1 is actually if it's below the foundation level, for this term is always submerged. And for this term, then we calculate the effective stress. However, if it is somewhere in between, then what do we do? 咁啊都係用翻個基本理念嘅啫，唔係攞平均數就攞個比例。OK， 好嗱咁如果啲水低過呢個咧，我哋就用 dry density。有啲水浸到呢度咧 ，dry density 啊，大家都知啦。唔係 dry 啊，即係 bulk density 啊。如果啲水呢度咧，我哋就用 submerge。咁 submerge 應該係 somewhere 咁樣啦。如果 somewhere in between 係點咧 ？Between D is greater than 0 but less than B. So somewhere in between. What do we do? So again, we very simple. We just draw a straight line between this and that, and then we just find the effective stress by interpolation， 即係用比例嘅形式揾翻唔同嘅深度。咁呢個咧個 density 係幾多咁樣？咁所以咧，你見到咧就係佢就係其實即係不外乎將佢化咗做呢個，跟住用比例，我揾到個平均嘅 effective stress。咁你可以背咗呢條式都得嘅嚇，但係背後嘅理念咧就好簡單，就即係用比例 base on 佢個深度揾翻嗰個平均嘅 density。就係咁啦。睇下個水位喺邊啊？個水位喺呢度咁攞個平均數嘅其實就係，即係佢水位喺呢度嘅時候咧就係咁多，水位喺呢度嘅時候咧就係咁多。咁如果水位喺呢度係點咧？咁咪攞翻個平均數啦。就係咁，即係呢個 formula 咁就係咁嚟嘅。So this is the idea of how water will affect the calculation, how water will affect the use of this formula. Okay, so basically there are 3 cases. So one case is Water is between here. One case is below, and the second case is actually between here. So there are actually 3 cases. Okay. So this is how, and then we will use this 平均呢個數咧，就 apply 落呢度啦 ，apply 落呢度。咁呢個容易啊，呢、個就如果啲個泥喺呢度，咁呢度一定係用乾嗰個啦，係嘛？因為上邊係乾嘅啦，即係用翻啲 common sense 去諗嘅問題。So this is the idea. Let's see if there's any questions from see more on this. 咁啊，再提多次啦。咁一陣間有少少時間都會講下個 facet test 啦。好，好，跟住咧就會講呢個叫做 general， 反而呢個其實應該係最重要，因為即係講真話咧，就呢個就係真係會用嘅啦。如果咧我哋睇 code practice 就係用呢條式啦。咁我哋呢條式咧就係可以 handle 唔同嘅深度啦 ，handle inclination 啦 ，handle 個 shape 啦。咁其實唔止嘅，咁啊仲有 handle 好多，例如呢個斜坡啦，咁啊或者個 foundation 你側咗啊，好多其他唔同嘅 factor 嘅，不過即係我哋簡化咗咧，就淨係講呢3個普通比較常見嘅foundation 嘅表現問題，即係嗰啲力。OK。好，如果冇問題咧，或者OK，得5分鐘啊。 Hảo, this was the time and place. It's all over. 哦，咁啊，呢個下晝我都唔記得咗填係幾點啊？有冇同學知道啊？我上網我睇到，OK，你等陣先，抄得翻網先。一表完叻，應該係2點嘅你要2點先。星期11月611月3咁啊，2點係啦。房間就係有寫嘅，啲房間冇寫房間喎，真係盧永係喎，應該係喎，盧同學冇喺度喎。咁係5月，唔係嗰日係2點5點，room 就係隔離嗰個 room 101。呢個就兩點半嘅6日1係盧永賢咧，都冇中午嘅，係喎，有2個學號。上晝有喎，係啊。我係楊同學都冇升到啲嘅。 好，咁啊繼續。好，咁啊assuming that you understand the Tersaki's basic concept, so this is the general bearing capacity equation. So this is the one that we will be using actually. So you will see the form is basically the same. The form is basically the same. And then there are some factors actually. And in this case, we have shape factors, depth factors, and inclination factors. But actually, in the actual case, actually, there are more factors to it. The equation is actually very long, but we just look at 3 factors. So, 仲有通常都即係仲有2個 factor， 不過嗰2個 factor 可能就比較都容易理解嘅，一個叫做斜咗，一個範基水唔係平嘅，係斜嘅，咁或者一個範基水喺個 slope 嗰度，咁都係咁做嘅啫，其實嚇，都係咁嘅即係咁嘅，都係咁嘅用法嘅。其實呢啲 factor 就係代啲 formula 落去啦嚇。You actually need to substitute different formula for this. Okay, so咁啊有一紮新嘅 table 啦，即係啲 factor 又進咗啦嚇。So you have to use different tables or different equations to find this bearing capacity formula. 咁你發覺咧，佢有個呢個 E 啊，其實就最主要佢有一個 spinal curve 嘅嚇，即係嗰個 slope surface 就係嗰個 spinal curve。咁呢條 equation 咧，你可以用effective stress parameter 啦，或者係如果你用 total stress 就可以用 total stress parameter 啦嚇。咁啊，仲要 consistent 啦，用佢呢度，同埋咩情形先至用 total stress， 咩情形之下先用 effective stress 啦。咁呢個嘅 table 就係重新再 based on 呢方面係重新再啦。咁嗰啲 factor 就係呢扎啦。咁啊 factor 咧就係隨住年份咧就有少少變更嘅。你睇到咧就係有啲唔同嘅 factors 啊。咁啊其實咧就要睇翻最 update 嗰個啦。咁啊暫時我哋最 update 就係嗰個啦嚇core practice 啦，或者可以喺同學度俾同學睇下啦。有成日有個咁嘅阻住。core practice。咁啊，香港嘅咁啊，係應該喺打香港都出到嘅，係啦，嗰個 building department 可以處理。OK， 咁啊就係呢本啦，咁就係 bearing capacity。咁其實我哋嘅 training 就係 train 啲同學識睇呢啲啦，咁佢就係 page 14 bearing capacity equation。咁我哋就 page 14。page 14。OK。咁啊呢度有講我頭先嗰啲factor of safety 點樣 ？OK 好，哇！咁啊真係見到嚇死啦！咁啊呢條就係一條 equation 啦嚇，咁啊都所熟面啦。 咦，唔可以寫嘢。咁嗰啲 factors 咧，1、2、3，應該係得4個 factor 咧，1、2、3、4。咁當然啦，如果你主要係 shape 啦、inclination 啦、influence of ground surface、tilting， 咁或者係啦 ，tilting 就係呢啲啦。OK， 咁就係呢扎咁嘅 equation 啦。如果係 drain 咧就係佢都唔同咗嘅。如果係 drain 同埋唔 drain 啊，可能就即係都照放人入去 ，OK， 人落去呢度就複雜咗啦 ，drain 同埋唔 drain， 咁就 shape factor， 即係如果係實務地出嚟就係呢條 equation 咯嚇。咁都隨時都不停 update 嘅，有機會嚇呢啲。我哋睇翻碌市呢個啦。就類似呢啲 shape factor， 咁逐個 shape，咁好明顯啦。我哋計啲數嘅時候咧，第一步就係要計咗呢3個 factor 先啦嚇。就呢個，咁全部都係 based on 個 friction angle 嘅，咁變咗可以代咗呢3個去啦。而跟住咧就 shape factor 逐個咁樣代呢啲 formula 啦。咁或者咧，好似頭先咁睇翻本 core practice 嗰啲 formula， 逐個讀嘅。咁不外乎咧，都係幾樣嘢啫，就係我要知啦，呢個 B 就 stand for 個 width 啦 ，always 呢個就係 stand for 個 length of 個 foundation 啦，咁呢啲要知啦，係嘛？咁呢個就係個深度啦 ，depth of 個 foundation 啦。咁就仲有就係 inclination。嗱，通常 inclination 咧，我頭先講噶啦，就係因為通常都係因為個 vertical load 同埋 horizontal load。咁由呢兩個咪可以揾到嗰個resultant 啦，我哋中英文叫 resultant， 係嘛？咁揾到呢個之後，咪知道呢個角係幾多咯？咪代翻呢啲數落去咧，就可以計到嗰個 factor 啦。咁就基本上係咁啦。呢 factor 就係 degree 嘅。咁唯一咧小心啲就係啲位咧就係radian。呢啲例如對啲 angle， 即係轉翻呢個 angle 出嚟嗰啲咧就係 radian。係得呢個位嚇，呢個位啦。我哋轉翻個 angle 出嚟，咁唔會係用 degree 㗎啦，咁用 radian。係呢兩個位嘅小心啲啦，同位置。 好，咁啊呢度有個 example 啦，咁我哋不如做個 example 就比較容易理解啦嚇。咁我哋就變咗係用 general equation 咧，咁變咗咧就唔使考慮即係 circuit 咁喎。做 circuit 咧，如果我哋要用 square 嘅四方嘅 foundation 咧，就要用另外一條 multiply 咗嘅方法。咁佢呢個就唔使啦嚇。咁啊，仍然都係用翻呢條式。咁呢個嘅 example 啦，咁就 loading 就係150，深度就0.7 incline， 咁啊打斜啦，打斜其實之前講過啦，亦都可能都係有個韓信嘅路，不過佢直情俾埋個 angle 你，咁你唔需要考慮嗰邊啦。foundation 個闊度唔知幾多，咁啊我哋就叫 B， 咁啊 factor of safety 係3。咁啊壓落嚟嘅 load 咧就150，咁我哋咧就睇下可唔可以用 factor of safety 係3嘅時候咧，就係 design 翻個 B 係幾多啦。咁啊有啲難度喎，可能要乜啲啊深術喎嚇。OK 好，咁都係 based on 個 basic concept 去做啦，就based on 個 friction angle 啦。咁啊 start with friction angle because it's given is 30 and collision is 0, and I think in this case there's no water, so we have one very less. We don't have to consider the effect of water in this case. So we have the friction angle, so we can actually from the table or from the equations that we can find these two factors. Okay. And then we try to find the factors or the shape factors, and then the depth factors, and also the inclination factors. Okay, so first of all, we'll look at the shape factors. 咁啊 shape factor 就係睇翻呢啲 formula 啦，咁啊 shape 就係C 就係0啦，所以呢個唔使理啦，因為 C 係0噶嘛，即係呢個 C 呢個 factor 係0啦，即係乘咩0，乘咩都係0啦。Okay, so this is the shape factors. 咁啊，我哋 so because 因為係 square 啦 square 咁啊可以約咗。我唔需要因為 B 我哋唔知嘅，其實 B 係unknown。So happen this is a square footing, so we